Extending elliptic curve cryptography for quantum readiness. Author is Kunal Abhishek.
Quite some more time until the PQC gets field trials and all. Hence the title is Extending Elliptic Curve Cryptography for Quantum Readiness. So how we have started with this problem statement. We have thought that like PQC has started in 2016 and it has got standardized in 2024 actually. And within this short span of time, they have come for a new standards and all in 2024. And eventually they are saying that ECC and RSA will no longer be useful as they are posing quantum threats on them. So our point is little different, and we are now going to discuss on that quickly. So the structure will be like that. I will asking two main problem statement questions, and in the conclusion section we will try to answer that. Meanwhile, we will speak on how the technical trade-offs and strategic trade-offs they are influencing the ECC to be retained for some more time. So the questions are, can we use higher order curves for some more time until the existing infrastructure can be migrated to the PQC level, or we should immediately have the PQC in place? So these are the two questions which we are going to see in this paper, and we will try to answer that. The contributions will be based on that only, and we will discuss on the. We have discussed on the status of the ECC and post-quantum thing with the scalability challenges in generating the higher order elliptic curves. Because higher order curves are not easy to compute, and it requires a lot of validation, crypto validations, as well as supercomputing powers. So technical and strategic trade-offs are there, which we want to argue on that, and to make a feel that higher order curves can still be taken up while the field trials of this PQC gets over. And we have presented a strong basis for that. So as the quantum threats has come, we have got two kind of things. Either we can increase the existing RSA and ECC, or we can directly move to the PQC. For that, let us have a look on the quantum programs of different players. IBM is one of them. In 2024, they have projected their quantum development program, where they say that the actual quantum computers with certain number of logical qubits can be developed in a timely fashion. So current years like 2025, we have got a kind of estimation of 1092 logical qubits with them. Then it has gone up to 2000 logical qubits in the next 10 years, 2033. So we have to now, if this roadmap is based on some good scientific estimation, then we can have a trade-off with the ECDLP problem, how it can be tackled in a kind of reasonable time. In 2019, Rotler of Microsoft has patented one ECDLP solving time frame. In that, he has told that ECDLP of a good curve like NIS and all, which are recommended, if its size is 521 bit prime field size, it will require 4,700 logical qubits, which is far higher than what we can see in 2033 as per IBM thing. So in the last bubble, you can say 2033, it is 2000 qubit, and here it is requiring more than 4,500 qubits. Subsequently, the requirement of Toffoli gates, which implements that thing, and circuit depth is exponentially growing up. And due to the problem of gate realization and all, it is not that easy to break ECC that quickly in practical terms. However, we have got a SATICOM challenge which is open since 2000 or before that, where they have clearly posed two different level of problems of solving ECDLP. Level one has got 109 bit ECDLP, and the other one is 131. 109 was solved in 2004. Till now, there is no solution offered by anyone for 131 bit. If the quantum PQC or something like that is, it can break it. There was a $10 million of reward for that. That is not easy. So that has not happened. The level 2 is still we cannot approach because it has started itself with 163 bit of prime field size. So what are the challenges which are making us to really think of how we can have a higher order curves? So there are three basic challenges. One is the need for sufficient hardware compute power. And the second one is the software programs, because you have to write a big, it requires a lot of Gaussian eliminations and all. And for that, your RAM size is more. It is required and all, and you need a massive parallelization. And that parallelization is also not very useful because each core will need separately huge number of, computing frequency. More on top of that, the cryptographic validations also plays a very critical role, because you have to be cryptographically validated to get such curves. So overall, the getting higher order curves is also not that easy, but it is doable, and it is doable in a very cost-effective manner. And that is where we point it, because in CDAC Patna, where I belong to, we have already generated 768-bit curve. And that too with a minimal, we have used our supercomputing facility for that, but it is doable. So the point is, until the post-quantum things gets field trials nicely and checked for a reasonably long duration, we should not jump directly onto that. So we come to the technical trade-off, what the figure says. So in the 5-year block, a 10-year block, 5-year block, 2024 to 2029, the standard says that you use RSA either 2048 or 4096 bit. That gives you a symmetric security level of 112 bits. Similarly, ECC is used for 256 bit and 521 bit. That gives 128 or 258 bits symmetric security. And PQC is also giving you 256 bit of symmetric security. Quantum computers, they really need to compute. Now the state of quantum development program is like it has got only 200 logical qubits, just 200. And it has got many, limited fault tolerance and all. So there is a need of much mature, full-grown quantum computers to be in place to really pose a threat to ECC or RSA. In the next 5-year block, up to 2034, you can raise the key sizes of RSA to 15,360 to get a 256 or higher bit symmetric security. Similarly, 521 bit of ECC will give you more than 192 and 256 bit security. However, as per the IBM roadmap, they would be getting 2000 logical qubits. That is projected. It is not sure. Okay, and if that is that they could do, it will be a threat to a RSA and ECC really. So up to 2034, there is no any such really a problem for you. But this breathing time, you have to get ready to come for a fully grown PQC kind of thing. So this is what the point I would like to make here. And the next 5 years, up to 2039, you need more than 15,360 bit of RSA, which will really produce high latency in the computation. you need higher order curves, 521 bit, which I am advocating here. And 768 bit, we could do it. So we have not put it in the paper, but in the experience, I am just saying it. And PQC may get better way of doing the error handling in gates and all. So then you can think of the practical threat to the ECC and RSA. Up to 2044, we expect that full-grown quantum computer may come with millions of qubits, and that will really real-world risk. So these kind of traditional ECC and RSA will not work for sure. Beyond 2044, we cannot expect until we have a massive change in their algebraic structures, which suits post-quantum or quantum resilience. Now we see the strategic trade-offs, what it says. In terms of the bit security, the symmetric security, RSA and ECC are 128 or 256 bit of symmetric security they are giving. PQC is also giving the same one. Then quantum safety, yes, RSA 2048 is resilient to 3000 qubits. 4096 is resilient to 9000 qubits. However, the ECC 256 is resilient to 2330 qubits only, because the discrete logarithmic problem what it offers is easier to solve by quantum computers than RSA. But with the PQC, as it is a new technique, it is still to be tested under the field trials. In terms of the strategy, like how much it was live or used in the field, RSA and ECC are quite old, and they have really faced good cryptanalysis with the classical thing. So mathematics is completely understood, and there is no any such problem with that. Only threat was coming to with a quantum computer, which is not realized in its full power so far. Training also, like ECC and RSA was in the market, so the people are already trained on it. But in case of PQC, we really need training, a lot of training to them. We have to make to them. So in this way, these things works. The comparison of this ECC and PQC thing. We compare ECC and PQC in post-quantum time. So maturity level, if you see, ECC is well established and standardized with the decades of deployments experience and cryptanalysis it has got faced actually. And PQC has recently, last year, it has got standardized. Quantum resilience, ECC is so far theoretically not there. Assuming that quantum computers are there, it is theoretically not safe, but the PQC is designed to resist quantum attacks. Key sizes of ECC is very short, whereas the key sizes of PQC is very, very high. So you have to deal with the performance issue. And then efficiency is the same way. Deployment, we have got ECC and RSA deployed everywhere in the TLS schemes, smart cards, TPMs, everywhere. And now we are gradually going to implement PQC, replacing them. But at the same time, we are not sure about the difficulty and the amount of security it really offers, what it claims for. We are using hybrid techniques, so one classical, one PQC. That shows our trust is also little bit in the dilemma, that we are not 100% sure that, okay, let's go with PQC only. So that trust is not there. And that comes with the field trials and the longevity you have in the market. And the transition risk is also there because ECC has well understood operational policies, whereas the PQC, you have to go through eventually this, the new two isogeny based curve as well as the rainbow. Both have received the successful break. So that really shakes us that be sometime in the field, and then let us have our critical crypto infrastructure using them. So that is what the differentiation I could make in this paper. Now the point comes that how you can be quantum readiness, you can exhibit a quantum readiness with ECC. So definitely you have to produce higher order curves, and for that you need a real good computation with you, good mathematics with you, and lot of software skills are also required. And then all the communication where you want to have higher order curves, this has to support it. so that there should not be any mismatch while they are generating sessions and all the handshaking and all are happening. And these new curves should be standardized so that global acceptance will be there and interoperability issues should not be there. Finally, what we asked the two questions in the beginning, we are now concluding here that when quantum computers achieve their full potential, theoretically secure algorithms will only be resistant to quantum attacks. But that will take time as per IBM roadmap and other people also. ECC is not secure against the source thing, but remains secure until a reliable quantum computer with millions of physical qubits becomes a reality to break the ECDLP. Now it is speaking about the physical qubits. So a number of physical qubits will be joined together to have one logical qubit, and there is no noise and also logical qubits are less. So we should not get confused with that. And using higher order elliptic curves will enable strategy decision makers to save immediate technology migration cost for a reasonably long period until a practical quantum computer is realized with millions of physical qubits. Finally, the conclusion is like this, that legacy algorithms can still be used to provide adequate quantum resilience for existing security infrastructure for a reasonably long duration. After that, you plan for a migration to the PQC. And by the time, let the PQC algorithm get matured through the field trials and testing, more testing. Thank you. I would like to have any questions.
Questions?
Again, first of all, congratulations for selecting this topic, because so far what we have seen is most of us being discussing about quantum readiness and telling that it's going to take a long time, but this is a wonderful collection of data with which you guys have worked. First, congratulations for that. So the questions are like this, okay? The first thing is, you yourself mentioned about the logical qubits, isn't it? So,
sorry, I could not get you.
See, at one of the slide, you calculated about 9,000 qubits in order to break a RSA. What was the calculation with which you arrived at 9,000 qubits?
No, there are some research papers, like you can see here. I have quoted one here. In my paper, it is listed. One I have put here, this one. Source you can see. There you can have this kind of a study. These are
this is perfectly satisfying graph. After this, there was one slide where you showed all of the RSA 256 and things like that, right, in a tabular column. There you have specifically mentioned 9,000 qubits. Yeah, I believe somewhere here.
Yeah, here I have not referred, but in my paper it is referred. So those study I have put here. So because here I could not show it completely. So
because I don't see a calculation of how you arrived at that. That's one thing. Logical, because as you said, logical qubits are coming up. So we may not even need 9,000 qubits, right? Maybe some 1,000 logical qubits should be sufficient to break. But all of us are waiting for it. But that was my question, not a concern. But how did you arrive at that? And after all that, right? The title of this particular paper, right? You say it is, what is the title? What is the title of the paper?
Sorry, I'm not able to.
No. Can you go to the title of the paper?
Extending,
right? Isn't that misleading? When you say extending ECC, it means you are trying to configure ECC in such a way that you are extending that to make it quantum readiness. But here, what we are trying to see is
for some period of time. For the next period, some
exactly.
10, 20 years of,
yes. I don't see it as an extension of elliptical curve,
not
rather
extension,
continuation
scaling
of
up.
Usage of elliptical curve. So the title of the paper was something that I had a concern. Yeah, good.
Okay, thanks. Any other question, please?
Do you work with IIT partner? Because I got phone calls with regard to some drones.
Yes.
I think you interacted with me.
Yeah, my team is there. Yes, they are interacting with them. Yes. Thank you.
Quantum computation, actually multi-prime RSA has been given. by Rothstein, multi-prime. That means instead of having just PQ2 primes, he said number of primes you can use, and then, but that was not accepted in the, that is not selected. Okay, do you think any future is there for that, like you were telling extending ECC, similarly extending RSA using multi-primes?
Yes. That is there, sir. We can do it. The problem is with the trust, sir. Until it gets field tested for a reasonable, long division, we cannot just like that we can take up, because already two protocols has got the Rainbow and Isogeny. They have got broken. So that is what I want to just indicate. That let it be. Thank you. Thank you, sir.
To present a memento to our session chair,